Okay, good morning everyone. So the idea is to keep this talk, very fun, interactive, and not at all technically intensive. So it might sound like I'm trying to be a spiritual guru here and telling you about the essential tools of life, algorithms, and optimization. So let's see how far, I can make my case towards becoming a spiritual guru. So, yeah. Decisions, right? I mean, driving us crazy all the time. We need to take decisions for like every little aspect of life. I mean, as my advisor Samir Khullar puts it, it's like decisions everywhere, right? Whom to marry, how to cook, and where to buy gas. So he thinks that we can actually solve the daily dilemmas of life one algorithm at a time. So let's see how far algorithms can take us. So now consider the case of Pooja. She is, really confused right now. She has to decide whom to marry. Now, there is a prospective candidate, Raj. There's also Rahul. And then we have the cool dude, SRK. And she really likes Raj. Rahul, nah. SRK, of course, she does like. But now let's consider her friend Neha, who only likes SRK and SRK only likes her back. The others are not even prospective candidates for Neha. So now is there a way to, find good matches for both Pooja and Neha according to the feasibility, according to their prospective candidates, so that everybody is happy? Everybody gets a match? Okay, so now we come to the how to cook problem. So clearly Pooja wants to get married to the man of her choice and she wants to be happy. But then, things are not that easy nowadays. You have to maintain a high popularity quotient. You have to entertain. You have to, host parties at home. So Pooja wants to host a party. And she wants to cook some dishes for her friends which are high in the popularity quotient. But now she only has a certain time left before the guests start to arrive. So how does she choose? And these are the 3 dishes that she can, she knows how to make. And each dish comes with a certain preparation time. So the problem that she's faced with is which dish or which dishes should she choose such that it is overall high in the popularity index. At the same time, she will finish preparing them all before the guests start arriving. But even before she can get to the how to cook problem, she has to get home. And gas is running low in her car. So she has to get to the nearest gas station so that she can refuel her car and reach home at the right time. But she doesn't know where is the closest gas station. And suppose GPS stops working in your phone, right? So now you have to come up with something. Can algorithms help here? Now here is actually my first question for you. Consider this situation of Pooja where she is at a crossroads. She doesn't know where is the nearest gas station. Gas is running low. So she has to do something to figure out, how she can, in the worst case, travel the least amount of distance to get to the nearest gas station without knowing anything at this crossroads. Does she go left? Does she go right? And what strategy does she use? Raise your hands and tell me. Suppose there is nobody on the road. Let's consider a really bad situation for Pooja. She's in a deserted place, nobody to be seen, GPS is not working. Now she has to do something. Think algorithmically. Yeah.
She should go towards her home.
Okay, but now she's at the crossroads. And so consider just solving this particular problem. You're standing, or Pooja is standing at the crossroad. You have to get to the nearest gas station. You don't know whether the nearest gas station is at the left or is at the right. But you want to come up with a strategy which will, in the worst case, incur you the least amount of travel distance to get to the nearest gas station.
We don't know anything about the gas station. How can you come up with a strategy? We need more information. We don't know anything.
Yeah, so in the worst case, that's why. Okay, so anyway, maybe we'll come up with other questions, but let me give you the solution here. So this is known as the cow path problem in literature. So the strategy here is, you arbitrarily choose a direction to travel 1 unit of distance in that direction. If you find the gas station, well and fine. Otherwise, you come back to the origin or whatever was the crossroad and you double now the distance that you travel on the other direction, the right direction. Again, if you find a gas station, your search terminates. Otherwise, you come back to the origin and now you double that. That means you travel 4 units of distance on the left side. And you continue this till you come across with the first gas station, and you can guarantee that in the worst case, you will travel at most 9 times the distance of your closest gas station. And what do you know? This is the best any deterministic algorithm can do in such a situation. Okay, so hopefully you guys are now more excited about what algorithms can do and how we can come up with strategies to solve these problems in life. So, as you can see, we have, yeah. Sorry? So you already came from the behind, and suppose this is like the dead end where you can only go left and right. So there is, so you know that you didn't come across any gas station while you came up to the crossroad. But the idea was not to solve the exact problem that Pooja is facing, but to introduce you to this particular cute problem in literature, where what do you do when you're standing at some origin or some crossroads and you don't know anything? You have to get to some chosen destination, which might be either on your left or might be either on your right, and you now want to come up with some strategy to optimize. What can you do when you have no information beforehand? So yeah, so there is, as I said, the need to optimize and decide.
Coming back here, once she go and she come back and go twice the distance here. Instead of covering all those, if she goes in the same direction, I think she'll find the thing.
But there may not be a gas station at all in that direction, right? And then she'll, yeah. Okay, so but as Nuth says, you cannot try to optimize everything. Then you'll always be unhappy. And all we want is, happiness. Otherwise, my spiritual guru career is at risk. So what do we want to optimize? We have to choose our criteria. Do we want a solution quickly? Do we want a solution at the lowest cost? Or alternatively, at the highest gain? Do we want the solution to satisfy all possible requirements, all constraints that I have imposed? So we have to maybe somehow compromise somewhere, pick and choose what are the criteria that we want to optimize and what are the criteria that we can relax. So some problems, so let's not lose all hope, and let me, so some problems have this nice combinatorial structure which admit some polynomial cute algorithms for this problem. So you can come up with quick, efficient algorithms to solve these problems optimally in polynomial time. There are other problems which are NP-hard, and for other problems, we are faced with new problems every day in research where you don't even know whether it's hard or polynomially solvable, and there's a challenge. But for problems which are known to be NP-hard, it is unlikely that you'll come up with a polynomial time optimal algorithm for such problems. So for such problems, we have to relax some of the requirements, and the technique typically used by approximation algorithms researchers is to approximate the solution such that you can guarantee the worst case suboptimality by an algorithm which will run in polynomial time. So, coming back to the whom to marry problem. Now, those of you who are familiar with the stable marriage problem, this is not the same formulation, but I just use the example of marriage to introduce, I'm just using this idea to introduce the idea of matching. So, then these green balls, so the green balls have some set of prospective candidates. So, the red balls are the prospective candidates for the green balls. And an edge exists between a green and red only if the red is a prospective candidate for the green ball. So go back, think about the previous problem, right, which we introduced in the beginning. Pooja and Neha, they are people in the green ball set, and Rahul, Raj, SRKs are the people in the red ball set. Now, is there a way to find, match these greens to the reds such that the maximum number of people are matched? So can we come up with a greedy strategy? So if you're familiar with greedy algorithms, then this greedy is not a new term. For those of you who are not familiar with greedy, it means like coming up with a strategy which is locally myopic, which is trying to locally optimize and come up with some solution. That may not always be optimal, but that may not be too bad either. So that is the idea that we are trying to say here. So our goal here is to maximize the number of matched vertices. So one prospective greedy algorithm I'm proposing is order the vertices in some arbitrary order and greedily match the next unmatched vertex to the first available neighbor. So let me maybe give you the answer, or okay, so maybe I'll pose this as a question to the audience. So what do you think in the worst case the greedy will do compared to an optimal solution? So the hint is, consider the two incident vertices of an edge. So in a matching, there can be only one edge incident on each vertex. So now I've greedily picked some edges. So how many, so does that give any hint towards? Yeah, so I mean, I'm not talking about this particular instance. So that's a, yeah, one, I mean, the right step. So I'm talking about for given any instance, can you say what is the worst case performance of the greedy compared to an optimal solution?
All of A will be matched to 1.
No, so the characteristic of a matching is only one edge can be incident on a vertex. Okay, so let me try to give you the answer in this case. So since I have greedily picked an edge, what I might have done is, I might have prevented the choice of two edges instead, right? So for each edge, there are two vertices that this edge is incident on. So if I had not picked this edge, these two vertices could each be possibly matched to some other vertex. Therefore, for each edge picked, I might have lost out on two edges, right? In the worst case. Therefore, the greedy will never be worse than half times the optimal solution. So now, try to extend this intuition that I gave you to the case of weighted graphs. So now the edges also have some weights associated with them. So we are not just trying to maximize the number of matched vertices, but we are trying to maximize the total weight of the edges chosen in the matching. So one prospective greedy algorithm that I'm suggesting is order the edges in non-increasing order of the weights. Basically, the higher the edge weight, we want to favor it. We want to pick it first. And we add the next unmatched edge from this list to the matching if it continues to be a matching. So remember, the characteristic of a matching is only one edge can be incident on any vertex. So as long as the next unmatched edge can be added to the current matching, we do this. So can we, extend the previous argument that I made in the previous case to say something about the worst case performance of the greedy here? Consider the non-increasing order, non-increasing weights order in which we are picking the edges. Okay, so again, we can use a similar argument. Oh, you have an answer? Yeah, you can try. I mean, yeah, so similarly, right? So just try to make that argument. So then I might have prevented the choice of two other edges, right? But what could have been the weights of these edges? Exactly, right? So for each edge chosen, the weight of this edge is at least half times the two edges that could have been chosen in the optimal solution instead of this edge, right? Therefore, this gives, again, a half approximate solution. So I think the two ladies jointly gave an answer for this, and they're up for the prize. Okay, great. Now, this is a question that I I will answer myself because I already got 2 answers in the previous example. So, so what if these edge weights are revealed online? Actually, you can show that this greedy algorithm in the weighted case will be arbitrarily bad. You know why? Just consider 2 green balls and 2 red balls, and maybe initially you first reveal the edge from the first. Suppose this P1 is revealed 2 edges to C1 and C2. C1, this edge has a weight 1, and this has an edge weight 1 minus epsilon. So you greedily match P1 to C1. But now maybe P2 is coming in with only a single edge of weight say 100 to C1. So now your optimal solution would have matched P2 to C1 and P1 to C2, getting a total weight of 100 plus 1 minus epsilon, whereas you only end up getting 1. So this 100 can be made to be arbitrarily bad, and hence the greedy algorithm in the weighted case will be arbitrarily bad in the online scenario. Now, there is an optimal way to solve this maximum cardinality matching, and also a way to solve the maximum weighted matching that we just discussed. So the key idea. Okay. So suppose, forget about P3 and C3. Suppose there are only 2 sets of vertices, C1, C2, and P1 and P2. Now, P1, initially 2 edges have been revealed from P1 to C1 and 1 from P1 to C2. This edge has a weight 1, and the other edge has a weight 1 minus epsilon. So you greedily choose a higher weight edge, and you match P1 to C1.
Details are not simultaneously available.
Yes, so the edge weights rather are revealed online. So it is like coming one after another. And now in the next time slot, a new edge is revealed between P2 to C1 and no edge from P2 to C2. And this edge has a weight very high, 100 or something, 1000, whatever you want. And therefore the optimal solution would have matched P2 to C1 and P1 to C2. Whereas you cannot do that anymore. So the key idea when we know in the offline scenario, when the edge weights have already been given to you, is to find an augmenting path to solve this problem optimally. So what is an augmenting path? It's a path that alternates between matched and unmatched edges and ends and starts in unmatched vertices. Consider this current matching, P1 matched to C1, P3 matched to C2, and this is a feasible matching because every vertex has only one edge incident on it. Now, what is an augmenting path in this scenario? This red path. So it starts and ends in 2 unmatched vertices, and it alternates between matched and unmatched edges. So now if we toggle, once we have found an augmenting path, if we toggle the matched and unmatched edges, we will increase the size of our matching by 1. So this is a key idea that these algorithms use. So I would encourage you to, if you're interested, to go and look up. So you'll find lots of lecture notes, tutorials in online, or you'll also probably learn about it in your classes. So using this idea of augmenting path, finding augmenting paths, you can find maximum cardinality matching in polynomial time and solve this problem optimally. And there also exists a way to do it for the weighted case, known as the Hungarian algorithm, that is very useful and used a lot in the literature. Let's come back to the what to cook problem. Now, Pooja has guests arriving in the next 2 hours. Now, she has to choose from a set of dishes that she knows how to cook, to what to cook. Each dish has a certain popularity PI and requires a certain time SJ to cook. So now, how should she pick the dishes or plan the menu such that the menu is prepared in 2 hours and the popularity of the menu is as high as possible? So this actually maps to the knapsack problem, which is a classical NP-hard problem. So the problem is stated as follows: given n items, each of profit Pi and size Si, which items shall we choose so that they can all be packed into a knapsack of size C and the profit of the items is maximized? So yeah, let's the profit of optimal solution is opt. Again, going back to greedy, which was the myopic strategy, right? Locally optimal strategy. Let's consider one greedy strategy. We want to maximize the profit, right? So we order the items in non-increasing order of profit. basically we want to pick the highest profit items first. And we pick the next available item that will fit in the knapsack. So, can you tell me how badly or how well this strategy will do? Can you come?
Half as good as the actual optimal result.
Actually, it is arbitrarily bad because, let me give you, anybody wants to take a shot at coming up with?
You can select the highest profit, but let us suppose there are others which have just one profit lesson, have silent profit lesson, and the time is very much less. And
Exactly, exactly. Yes. So, another price. Yeah. Great. So, yeah, that's the key idea. So, we have, say, one one item of profit 1 and size C. And we have C items, each of profit 1 minus epsilon and of size 1. So, if we just use this strategy, it will be unbounded. So, I think I have already exhausted my budget of prizes. So, the next, so I'll try to give the answers myself. Okay, maybe another prize for this one if you can answer. Now, so the previous example showed that we somehow have to be aware of the sizes, right? We can't just blindly look at the profits. So now if I want to use a second greedy strategy where we are ordering items in a non-decreasing order of size, basically we are trying to pick as many items as possible. Start with the smallest size items and pick the next available item that fits in the knapsack. So how badly will this do?
We can have many items with less size, but there's some profit is less than just one item with a very big size and very big profit.
Exactly. Okay. Yeah, this is it. Yeah. No more prizes. Yeah. Great job, students. Yeah. Okay. Great. Yeah. So, yeah. So therefore, we somehow have to be aware of both the profits and the sizes in solving this problem, even when we are coming up with a greedy strategy, which will not be optimal, but we somehow want to bound how badly our solution is doing. So I'll tell you that this algorithm has an approximation ratio of half. So maybe you can think about later why this will do half. So the algorithm is quite simple. Instead of just considering the profits and the sizes, you consider the ratio between the profits and sizes, and you order the items in non-increasing order of profit over size ratio. You want to pick items which are more profitable for the same size first, and we pick the next available item in the list that fits in the knapsack till we come across the first item which will exceed the capacity. And let this be called the last item that we put in the knapsack. So now you compare which has a higher profit of the two, the set of items till we put the last one in or the last one. And you pick the higher one of the two to fit in your knapsack. And try to prove that this will give you at most half in the worst case. So the traditional, so there is actually a better approximation algorithm for a knapsack problem, which is one of the easier NP-hard problems. So we call this technique as FPTAS, or a fully polynomial time approximation scheme. So basically, you can come up with some dynamic programs which will run polynomially dependent on some factor epsilon that you choose, while losing the accuracy compared to an optimal by an order of epsilon. So there is a way to solve this knapsack problem as I described by a dynamic program, but the dynamic program will have a time complexity n square p max if we do not do this epsilon strategy that I said. Now, is this polynomial? So if the highest profit is some function of n, where n is your number of input items, then this is considered polynomial. However, that is generally not the case because Pmax can be arbitrarily large. And in this case, this is considered to be pseudo-polynomial. And we know that, of course, no polynomial optimal solution is likely to be possible. So what we do is, since profits can be very large numbers compared to input size, we have to somehow reduce the profits by tolerating some loss in accuracy and then solve it on the reduced instance, which you can now do in polynomial time. So I will not go through these details. Again, you can look up a lot of stuff like literature online and maybe in your course material, which will give you how to solve the FPTAS problem for Knapsack. The key idea, as I said, is to make the profits as some function of epsilon and n. And now the profits are kind of appropriately reduced to be functions of only n and epsilon. So for a fixed epsilon, 1 over epsilon is considered a constant. Now we can solve the dynamic program, which will have a time complexity as a function of n and epsilon, and profit loss of at most order epsilon. So this is what is known as polynomial time or fully polynomial. Yeah.
You are considering the profits are functions of n, function of input size.
No, we are not considering profits to be functions of n and epsilon. What we are doing is we are considering reduced profits, which we have now made to be a function of epsilon and n. Basically, we have defined this quantity, say k. Now, if you define every profit by k, you can see that the maximum profit in this reduced instance will be what? N over epsilon. So now the profits, instead of being arbitrary numbers p, have been reduced to some functions of n and epsilon. And now we can use the dynamic program that I described previously, right? So p max will no longer be p max, it will be some function of n and epsilon. And therefore a dynamic program can be used. So this can be a slightly confusing concept in the beginning. So you'll probably have to, and I don't have enough time also in this lecture to go through this in details, but I'll be happy to talk about it afterwards. So again, so we are defining some k as epsilon times p max over n. Now we divide all of the profits by this k. So now you can see, consider the highest profit item. What will that be? Value p max divided by epsilon p max times n. So which will be n over epsilon. So all other items will be at most n over epsilon in profit. And therefore now we can use a dynamic program. So now finally coming back to the gas stations problem, right? So moving away from Pooja's viewpoint. Yeah, sorry.
Just the factor of p max goes to low, right? You are saying if we go of n square p max, but if I am using a 2D matrix or something to use the dynamic program, I can take little more n square, right? So where is the factor of p max coming in the...
So the traditional dynamic program, I mean, if you try to write a dynamic program for this, you will see that it will have the p max or the maximum profit will factor in somewhere into this, because if you always you're trying to choose the next find a optimal solution for the next sub problem, which will have that p factor in. So you will have to do a minus p or something. So basically one dimension of your matrix will be p max, and you will have to have the p in a dynamic program. So that is why it becomes a non-polynomial. You cannot do it in terms of it. Okay, yeah, gas stations problem. So we already looked at some solution that Pooja can employ, but now coming back, looking at this problem from the point of view of the city authorities. So where can the city set up gas stations, so that everybody is happy again? Again, as Noop said, we cannot try to optimize everything, so we'll have to relax some things. So now the city authorities will incur some cost in setting up gas stations. So they want to minimize the number of gas stations they want to set up. And there are some candidate locations. So the cost of setting up one station in location I is some SI. But we need to serve all customers, and they should not have to travel too far from their home location to get to these gas stations. So we consider a customer to be served as long as she is located within a distance d of a gas station, of a prospective location. So now how do we choose the locations for setting up this gas station so that everyone is served and the overall cost is minimized? So these stars are the candidate locations for the city authorities to set up the gas stations. And these people are the people who will be covered if you set up a gas station in this particular location. These are circles of radius d. I said that if this person is located within distance d, they are all covered. So this is an optimal solution for this example. Now let's consider a generalization of this problem and study that. So consider you are given a universe U of n elements, and you also have a collection of subsets of these items. So S is a collection of subsets of these items. Each subset has an associated cost, Ci, and also covers some set of these elements. Each subset contains a set of n elements and has an associated cost Ci. Not all subsets will contain all n elements. Now we have to find a collection of subsets of minimum cost. such that we cover all of the items and yeah, all of the items in U. So let's see, do I have any more, is it possible to ask another question? Yeah, okay. So the final question, can you suggest a natural greedy algorithm? Yeah.
What all the subsets are there cost, and then we such that there do a difference between the next possible way of subset with the applied subset. If you just transfer input that into the subset.
So you're almost there, but should we only consider the cost? Because the sum. Difference of the subset.
We should consider disjoint subsets or subsets which have minimum number of overlap.
Okay.
If I have a subset with 6 elements, 1 to 6, and its cost is the highest, and the next subset is 1 to 3 with highest cost, second highest cost, but they are overlapping. So there is no point in considering the second one.
Right. But then how are you choosing the next subset?
The disjoint one.
Okay.
This could be covered in the difference of the applied subset and the next subset.
Okay. I have another person trying there. Yeah. But that will not be polynomial. The idea of coming up with a greedy algorithm is always to come up with something efficient. So maybe what we'll do is, since there were, okay. Okay.
We can take size upon cost,
Mhm.
and then we can arrange them according to that. We want the maximum size and the minimum cost. So, and then we can basically take the next disjoint. Once we've arranged it, then we can take the next disjoint subset that we can consider in this particular.
Okay, so this was a collaborative effort. So the prize doesn't go to anybody, but I think this was a great effort by everybody. And we have finally come up with what is a natural greedy algorithm for this problem. Pick the most cost-effective set. So the cost-effective set is, so which is a set, basically you look at the ratio of the number of items covered divided by the cost. And then you pick the most cost-effective set. Now you remove all of the covered elements from your instance. Now you have to recompute the cost effectiveness of the remaining sets. So somebody suggested, the lady suggested, right, the disjointness. So we may not have disjoint sets, but we enforce the disjointness by removing some of the elements covered already, recomputing the cost effectiveness, and we repeat this till all elements are covered. Now this unfortunately has a very bad approximation factor, order log n times opt. But this is probably the best you can do for this problem in polynomial time. So there has been a lot of results in complexity which show that that this is probably the best you can do in polynomial time. Yeah.
How are we choosing the most cost-effective set if we are not considering all the two variables?
So you are given a set of subsets, right? So you only consider those M subsets. So if this is a part of the input, so you're okay as long as you can consider like you will go up to M. So as a part of your input, you are given a set of M subsets that you can consider. So among these M is considered therefore polynomial. Yeah. Okay, now I'll introduce the last technique that I want to talk about before I start talking about some of the work we are doing at Xerox Research, where I'll tell you about some industrial research problems. So for the set cover problem, we saw a greedy strategy, right? There is another very nice, elegant way of approaching this problem. So this technique of integer linear programming is an oft-used technique in optimization and algorithm design. So I don't know how many of you are familiar with writing linear programs or integer linear programs. So let me try to explain what I mean here by this set of notations. So let xi be some binary indicator variables, which is 1 if your subset Si is chosen in the solution. And Ci is the cost of a subset, right? So your objective is to minimize the total cost of subsets selected. So that is why you look at the minimization of the summation of xi times Ci over all subsets Si in S given to you, right? So this is, objective part is clear, right? Now you have to make sure that all elements are covered. So this is what this constraint here trying to do. That for every element J in the universe, you have to make sure that at least one subset that J was a part of has been chosen as a part of your solution. So this is what this is trying to capture. So if we can solve this optimally, this is clearly the optimal integral solution for the set cover problem, because this is capturing what is it our objective, and what are the constraints that we want our solution to satisfy. And let's call this as ZIP, as an optimal solution to this problem. So now if you have access to an ILP solver, so there are some integer linear programming program solvers out there, then you can solve this for a given instance and solve your problem optimally. The problem is, ILPs generally take very long time. I mean, it's generally NP hard to solve integer linear programs. So there is no efficient way to do it. So if your instance size becomes large, then you cannot use even these commercially available ILP solvers, the state-of-the-art solvers. It will take days sometimes, maybe it will crash, run out of memory, and may never terminate. So the technique is to relax the ILP to a linear program, where previously we had said that xi's are integer binary variables, right? It can only take values in 0 to 1, but now we relax them. We let them take fractional values. So now xi can be your, half, can be 1/3, whatever. And this problem can be solved by solvers in n polynomial time. Let's call the optimal solution to this problem as ZLP. Let's denote its cost as ZLP. Now, I hope this statement is obvious, that the cost of ZLP will be at most the cost of ZIP. This is because an integral solution is always a feasible solution for the relaxed version of the problem. So the cost of the integral solution can never be lower than the cost of the fractional solution. So now, often what we do is, we relax the ILP for an NP-hard problem to an LP, and then we round the solution of this linear program. Round means we have to somehow, we cannot do with fractional allocations in reality, right? So we have to allocate things integrally. So now we have to round these fractional variables that the LP solution is throwing you in some principled manner, while you're guaranteeing the total increase in cost compared to this linear program solution. Now, if you can bound the increase in the cost by rounding as, some C times the ZLP, that will also give you a bound compared to your, it will translate to a bound as C times opt, right? Following from this inequality. Because if your rounded solution is at most the cost of C times ZLP, ZLP is at most ZIP, which is equal to opt, therefore the cost of your rounded solution will be at most C times opt. So, one rounding, so I'm giving you some information about the instance that we have given you. Consider an instance where every element in the universe is occurring in at most F sets. So now, find the linear program solution for this instance. And a rounding I'm suggesting you is, pick every set Si with xi greater than or equal to 1 over f. Why is this rounding? Because I'm saying that for any xi which has fractional value at least 1 over f, you set that xi to 1. That is, picking every set means setting that xi to 1, and that is why this is a rounding. So, since we did not have any prize winners for the previous question, for the last question in my talk, can you tell me, will this be a valid set cover? And what is the cost of such a solution compared to opt? So again, the hint is every element will be occurring in at most F sets. And we are picking every set with xi greater than or equal to 1 over f. Anyway, in the interest of time, I guess we will, I'll give you the answer. So yes, why is it a valid set cover? Because now that we have picked every set which has xi at least 1 over f, we are sure, and each element is occurring in at most f sets, we are sure to have covered every element. Because we are setting every xi, which is greater than or equal to 1 over f, we are multiplying it with f in some sense, right? Rounding it up. And therefore, every element will get covered. So maybe think about this after this talk. And what is the cost increase compared to opt? So since we have rounded it, sort of multiplied this by at most f, so this will reflect here in the cost, right? So the cost will be increased at most f times. And hence, this will give you at most an f opt solution, which is a valid set cover. So now I'll tell you something about, so far I've talked about different, optimization and algorithmic techniques, which are fundamental techniques and interesting approximation algorithm approaches which people use both in industry and academia. So now I'll just quickly give you an overview of some of the work we are doing in Xerox research, where you'll see how we are trying to apply maybe some of these techniques, maybe some other techniques into solving some real life problems. As Adirupa mentioned, I work in the transportation domain mainly in Xerox. But as you know, I did my PhD in algorithms and approximation algorithms. Therefore, I'm always looking for opportunities where we can apply algorithms to solve the daily dilemmas of life, as my advisor puts it. So, share a ride. So this is a project where we are looking at ride-sharing solutions for urban mobility, for mobility of the urban millennium. So how did we get started on solving this problem? So currently, as you know, given, I don't know if you're familiar with the traffic situation in Bangalore. I mean, it is a mess, right? I mean, it is like really crazy. You cannot get anywhere in less than 2 hours. So therefore, we wanted to look at how do we solve this transportation woes of this problem. And it turned out that a bulk of this traffic is because of this people going from home to office and back every day. So Bangalore being the IT city, there is this huge volume of people who are going to and fro work. So we were working in a problem in public transportation, trying to optimize some routes and schedules of some buses and trains in Latin America, when Xerox services themselves approached us with some help with this employee transportation problem. So the problem was, let me show you by example. So you may be aware that many service delivery organizations offer employee transportation as a perk to their employees. So this is roughly the problem. Suppose this is some location of the office somewhere in Chennai. Services is located in Chennai for Xerox. And these are the 7 employees who get done with their shift at say 5 p.m. and they need to be dropped to their home locations given by the positions in the map. So this, as you can see, offers a very interesting optimization problem. Now Xerox has to spend some money per vehicle and money which is dependent on the time, the distance traveled by each car. So the problem is, how do we find the right set of people to put in each car and what is the route that each vehicle should take so that the overall cost is minimized. Again, and now, even if we have solved the static problem, given all of the information beforehand, we have solved the static problem optimally. Now, what Xerox was seeing is they were getting these cancellations in real time. Say, 5 minutes before 5 p.m., maybe somebody calls in to say, sorry, I cannot leave at 5 p.m. today. I'll be leaving at 7 because I have work to finish. So now, suppose in this instance, we have 3 cancellations. Should we still, leave this car going with just a single passenger and spend all of this money? Or can we do some dynamic optimization, which works real time, very fast, such that, we can accommodate the 1 passenger left in the second car in the vacancy of the first car with a low increase in the detour of the first car, thus bringing the cost down optimally. So we realized, so I'll not go through all of these details because I want to give a brief overview of all of the different things we are doing. So basically we realized that this is not just applicable to employee transportation, but the problem we were looking at was really ride sharing with either a single pickup point or a single drop-off point. So now for the offline problem, when you know all of the information beforehand, what we did was we went back to this integer linear programming based optimization algorithm. But then, how to solve this online problem when we are getting these new requests and last minute cancellations. So what we did was we used a technique which is quite similar to the maximum weight matching that I described earlier. So instead of maximum weight, you can also do a minimum weight matching in polynomial time. So what we did was we tried to come up with a way of matching new requests who do not have, which have newly come into the vacancies of the existing cars at overall as low a cost as possible. Then we wanted to look at the more general problem, where requests are coming up at different parts of the city, and each requests have some time, wait time tolerance. I need a car, but I'm not willing to wait for more than 15 minutes. Maybe I'm a nice person. I'm willing to take other people to ride share with me while I'm going from home to office, but I don't want a detour of more than 2 kilometers. And maybe Adi Rupa is a nice person too, and she wants to be all environmental friendly, and she wants to opt for ride share with me, but she doesn't want to walk more than 500 meters. So now we have all of these constraints that are coming up in this problem, right? And we want to optimize certain things. If we are doing it for the service provider, so in industrial research, always there has to be some kind of a business alignment, right? And that fits in very well with the different optimizations that I already spoke about. So we want to maybe maximize the revenue of a service provider. Or maybe we want to maximize the vehicles, utilization of the vehicles. Again, while you can solve it optimally by an ILP, we saw that quickly it will not scale. I already said that, right? The ILPs do not scale. So we had to come up with some greedy heuristic. Now, why I say heuristic is because, sometimes in industrial research, you may not be able to prove a worst case guarantee for the problem that you're faced with. And especially it happens if it's an online problem where requests, nothing is known beforehand. But you have to come up with some heuristic, maybe using some of the techniques you've already learned in algorithms and approximation and optimization, which will end up giving you a pretty good solution in most cases. And you want to show that also empirically. So we actually came up with a real-time, very fast, greedy algorithm, which uses some dynamic programming techniques from the literature and interval scheduling to solve this problem in a completely online manner as well. So since I did not speak about interval scheduling in this talk, I will not give details about this. And we actually showed that by comparison with the ILP on small instances, the greedy algorithm, though it is a heuristic, it is performing quite well to the ILP for the instances we considered. And here you can see a running time comparison, and this is in log scale. So you can see the ILP can, sometimes take 6 to 8 hours, whereas the greedy will run in like very fast, 0.1 seconds or something. So now what we wanted to do is move away from just the optimization problem and look into more systems building, where we wanted to build a peer-to-peer ride-sharing system integrated with a multimodal trip planner. At that time, what we saw was most multimodal trip planners, say Google or whatever else you might be using, they're offering choices in scheduled modes of transport, such as maybe buses, metro, and walking. And there are these ride-sharing services which exist in isolation. In the US, it's like a big thing from a long time, Super Shuttle, Uber, Lyft. And in India now, Uber and Ola are doing ride-sharing big time. But then the trip planning solutions do not allow ride-sharing as one of the modes or one of the legs of a journey. And we thought that is what is probably missing to get more people to adopt public transportation, because often we don't have first mile or last mile connectivity, and we end up taking our own cars. Instead, if we could have this platform where, people could push their supply, like I'm interested in offering a ride share from here to here, these are my constraints, and somebody else now comes into the system to look for a ride or look for a trip plan, and if everything matches, then she can hop onto my car, and we are actually getting, more cost efficiency and better vehicle utilization while also ensuring the connectivity. So, at the same time, what Xerox, this was very well aligned with the business interests of Xerox, and Xerox has already launched a multimodal transportation solution, though the ride-sharing part of it is not yet integrated into it. So we launched something in Los Angeles and Denver in the beginning of this year, and we've also launched a multimodal trip planner for Bangalore, which you can find in the App Store and Play Store currently, and it's a beta version. So why don't you, you have a question? Oh, I thought, no. Okay. So I would ask you all to go to App Store, Play Store, install this and give us feedback for this app. So this is the back end of the rideshare system that we built, and we had to come up with a layered architecture and some modes of integration with a multimodal trip planner, so that we can make an infeasible trip plan feasible. So if you're interested in getting more details about it, you can write a mail to me and we can talk later. So again, this came up with some optimization problems that were thrown up at us. So we wanted to make the system as a completely dynamic one. Like even when I have started on my journey, now if somebody's request is coming up and based on my current location, detour already incurred, this is a feasible request to be matched to me. And maybe I have other constraints. I only want to ride share with women or Facebook friends or my work friends or something. Everything has to be matched. Then even in real time, we want to be matching such dynamic ride share requests. So now we could not just update the information in database and query the database every time, because that was leading to a lot of performance issues. I mean, then you can't have a real-time system. So again, we came up with some ideas as to how to store this information in memory itself without having to query the database, and do it with at most a certain error tolerance. So again, going back to many of the optimization techniques we were talking about, right? When we cannot maintain all of the information, the entire space of information, we want to reduce the space of information within some epsilon error tolerance or guarantee, so that we still, the size of the instance becomes small. And then the idea we employed was we use this, described somehow the underlying geographical region, store the information in a hierarchical manner with grids at the lowest level, then landmarks where each landmark is kind of covering a set of grids, and a cluster of landmarks on top of that with the property that no two landmarks in a cluster are more than a certain distance away, and we wanted to minimize the number of clusters that we want to store in the memory. So this turned out to be as hard as set cover. Remember the set cover problem I just described? And then we use some two approximation algorithm for an existing problem to get a bi-criteria approximation for this problem. And then, and the last two threads maybe quickly. So even if you have solved the routing and matching problem optimally, there's this problem of pricing, right? So that people are incentivized to opt for rideshare. So how do we split the costs in a fair manner such that everybody is happy? In this example, S1, S2, and S3 are the three ride sharers, and D is their common destination. So total cost of the trip is S1, S2 plus S2, S3 plus S3D. If we just split the cost evenly in every leg among the people who are in the car, while S3 is going to be very happy, she is like incurring a third of her best case cost, the others are not going to be very happy, because they are taking a huge detour and potentially paying for that. So we came up with some cost sharing mechanism where passengers will be compensating others for the detour inconveniences that they are causing to the people in the car, and the matching will only be valid if it is sequentially individually rational. What I mean by that is, for every additional pickup, the estimated costs will only go down for all of the people in the car, and of course it will be low for the new person. And now every person can actually specify the rate at which he or she wants to be compensated for the detour with a maximum threshold on the detour. And if all of these constants are identical, we show that this can be ensured, this fair rationality can be ensured by this nice inequality, where you, for determining the feasibility of the ith match or the ith pickup, you only look at the previous one, I minus 1. I'll actually show you how this helps us. So basically this, what we call the teardrop inequality, gives a feasible region for the next pickup such that it will still be fair and rational for everybody, maintain the rationality property. So I'll just show you how this teardrop inequality will look in Euclidean space. Suppose this is the source and the destination for the first passenger. Then this gray area given by that inequality in Euclidean space is a feasible region where your next pickup can be while maintaining the rationality properties. So if your next pickup is somewhere here, then the teardrop inequality will be appropriately reduced because you've already taken a lot of detour, you see. So you can only, so this is now going down. So I've already talked about this. So yeah, the one nice point is if you look at the inequality, it is reinforcing intuition, and that is the beauty of math many times and optimization. That you can see that the feasible region is inversely proportional to I. So the more passengers you have in the car, the feasibility of a match only goes down. And also, it is directly proportional to the distance to the destination. So the closer you are to the destination, the smaller is your feasible region, which is again intuitive. And maybe I can show you, this actually works in an online manner. So this is a mocked up example where suppose somebody has been picked up from the airport, and this will show you in I don't know why this is not playing. Yeah, so you can see the first customer's meter is now increasing, but I'll maybe do it to the first detour and then I'll stop. So the moment the second passenger will start getting picked up, the first passenger has already made some savings because of the detour. So it is also and the second passenger's meter is now increasing. So it's a visually compelling way. You know, if you see in your app that, okay, I'm saving some money because I'm taking this detour, you might be more, interested in opting for it, and you will not feel the inconvenience so much. And the same thing will happen when the third detour will start. So now the first and second passengers will go in yellow, and the third passenger is going to go in red. And the final question we looked at is that how do we figure out the compatibility between ride sharers? Because we did some surveys and figured out that people are often concerned about, who will I be sharing rides with? Will I like it? Will I like that experience or not? So this compatibility problem, we showed that this actually maps to some kind of a graph partitioning and learning problem. So of course, we wanted to have something to do on the product side as well, because we have to somehow estimate it. So this is the idea we had on the feature side, where just like you rate your Uber and Ola ride, after the ride share is over, you will just rate by, number of stars. How was your ride share experience? Without going and rating each and every individual, because that can be, feel a little bad that you're rating people, but you can rate the experience. And then we use this information somehow. So suppose these vertices are the commuters and the edges have weights denoting their compatibilities. So using these ratings, we try to estimate what is the right edge weight, and then suppose you know all the information, how do we partition these people into certain size graphs, or find out the right ride share groups such that the happiness index is something we defined is as high as possible. So the happiness index is what is the happiness of the least happy pair of users. In this case, it is 3. In this case, it is 4. So, we came up with some algorithmic solutions for this, and if you're interested, we can talk later. So, and this was some empirical study we did to show that this is how fast we are learning the weights, and this is how our greedy heuristic is comparing to an ILP solution. So finally, I'll end my talk with again asking you to go and look at the Go Bengaluru app. And also, if you find any bugs, just shake your phone to report the bug and tell us. So hopefully I have been able to, give some idea about algorithms, optimization techniques, excite you about how you can apply them in your daily life, and also use them going forward in industrial research. Hopefully all of you will go to, do PhDs, get your PhDs and masters, and do some great work in the future. Thank you.
Thanks a lot, Koyel, for the absolutely fascinating talk and helping us solving our daily dilemmas of life. I'm sure we have a lot more actually, and so we would love to hear from you more. So.